Good morning. I want to speak you about the alternative to calorimetry. First, what is the team? John Giles is an old engineer. I was a molecular biologist at the beginning, but when I was a student, I was listening to the lecture of Jean-Pierre Vigier, who was the main disciple of Louis de Broglie. And I also listened to the lecture of Professor Mariusz Szemla, who was the disciple of Nobel Prize Joliot-Curie. So we have a great respect to the classical physics. So our motto is no new particle, no weak neutron, nuclear force, nuclear interaction stay strong, and weak interaction stay weak. Since the first publication of Martin Fleischmann and Stanley Pons in 1999, the majority of articles in the LENR field have focused on calorimetry. Many calorimetry are masterpieces of science. Nevertheless, despite the experimental evidence, the results indicating excessive heat have not convinced the scientific community. It's a little forget, this fact is little forget, but at the time of Marie Curie, the main evidence was not radioactivity, because at that time there is probably only 10 people in the world who know what an ionization chamber was. It was not the light, the beautiful light of radium salt, because at that time there is a lot of chemical, of phosphorescent chemical. The main scientific evidence was calorimetric experiment, but at this time it was only heat, not excess heat, and it changed everything. We are facing a difficult struggle since year, and the main efficient tactic in the battlefield is crossing fire. So we must crossing fire of calorimetry. We must cross fire with tritium detection. We must cross fire with helium detection, and I want to suggest 3 other technologies to cross our fire in order to win. During the 20 last years, a lot of new alloys were discovered by the people of the field of the metal hydrogen batteries. There is some alloys, there is other alloys. Some other alloys are better than palladium in terms of hydrogen hydrate property. So we need new method, a new simple method, simpler than calorimetry, to sort the better alloy for our LENR experiment. For this purpose, we propose 3 relatively simple techniques. First, the fusion diode effect. When a deuterated alloy are in contact with a semiconductor, we can see the appearance and an easy-to-measure electrical voltage. And if this voltage actually due to a direct conversion of LENR or of a chemical artifact, it's not clear now, but if it is a direct conversion, we have a simple method to select the most promising alloy. The second method is related in the Reifenschweiler effect. It is the variation of the tritium beta ray Bremsstrahlung conversion efficiency as a function of temperature. But it is also a relatively simple method. And the third method is more prospective. It is an hypothesis that we have postulated but not yet observed. And it would make it possible to very quickly test many new alloys. The fusion diode effect. It is very difficult to make good calorimetric recording. It is more easy to count X-rays. But the more easiest way to get scientific evidence about any kind of phenomena is to do electrical recording. So what is a fusion diode? A fusion diode is made of metal, for example, palladium, in close contact with a semiconductor. It is a rectifying diode. When LENR in reaction takes place in the metal, at the beginning, we have high energy in the range of the mega electron volt, and then the down conversion of Professor Egelstein occurs, at the end, we have thermal energy. But before, the energy was totally down converted into heat. The energy will match the level of the excitation of the electron in the metal, and there will be a production of a pair of electron and hole, like in a solar cell, but inside our fusion diode. So it is like a fusion diode, like a solar cell, but the energy the source of the energy is LENR. What is a solar cell? It's simply a diode of large surface. It could be here silicon or metal, and here it could be a semiconductor, an all conductor. But it is also possible to do electricity with beta ray. For example, it is the idea of our colleague, Professor Miley. I take this picture at the IAA meeting in 2010. And Professor Miley made a lot of work about what he called beta voltaic battery. A beta voltaic battery, it's like a solar cell, but it's a solar cell in the dark, in contact with a beta emitter, and it produces a current. It is also possible to make electricity with electron beam. So it is very easy to record the voltage and the intensity of the resulting current at the positive and the negative side of the diode. And this sample device allows a simple recording of the total output power, because there is no electrical input, there is only output. So we plan to record this electrical energy during months or even year, of course, to exclude the possibility of a chemical origin. There is also no thermal input. We have published our result with the silicon on palladium as a metal, and we have also tried other semiconductors, like aluminum nitride or organic semiconducting ink. We have only published our experiment with silicon. It's the claim of my first patent in 1991. It is a wafer, a layer of palladium on the surface of the wafer. Here it is my first experiment. It was my first negative experiment. All the experiments were positive. It is an highly reproducible technique. Here it is a palladium anode, a conductive solution, a thin layer of palladium, a silicon wafer. Here it is the field inside. Of course, the field is quasi-null inside the anode. It is weak on the solution. It is null inside the layer of palladium, but it's very high at the junction. Because if we have 1 volt in a junction of 1 micron, we get a field of 1 megavolt. and the thickness of the junction is probably lower. So we have probably a field of a dozen of megavolts. So it was the experimental device, but it don't work because inside of a beautiful mirror of palladium, I only get a very bad suit of palladium. I made this experiment in the laboratory of the Eurobio company on the south of Paris in 1991. This is a fusion diode. Here it's a scintillator, and here it's a... So this experiment was negative in terms of generation of electricity, so I didn't publish. So in order to get a surface of junction as large as possible, our fusion diodes are made of powder diode. What is a powder diode? It is a tube, metallic tube, an insulating tube inside. Here it is pure silicon, here pure palladium, and a gradient of silicon and palladium inside. It's like two little trees, one tree of palladium, one tree of silicon, and there is a large surface. All the leaves of the tree, it's a poetic equivalence. All the leaves of the tree are in contact. So we get a voltage. It is my first experiment using a strong tube used for high pressure liquid chromatography. Inside there is a nickel powder. I use French nickel coin to make the powder, and also silicon powder. And I pressurize this tube with, here there is I put a little cylinder of pure sodium, and here I put some drop of EV water. And of course, the EV water follows the path through the powder, and we get a huge, very huge pressure of palladium. So the pressure was sufficiently huge to pop up the polyethylene cap, probably more than 1,000 bar of deuterium. But we get voltage. And this one, I made this experiment in 1995. It is also on a drawer, and it is still possible to see a little voltage. Chemical or nuclear, it is a question. So we made other type of fusion diode. Of course, we made control experiment. Here it's a fusion diode filled with deuterium. This one was filled with hydrogen. This one was filled with argon, and we get this type of result. With deuterium, we get a voltage as high as 0.5 volt. With hydrogen, we get a little voltage, and with argon, we get no voltage at all. Is it chemical or nuclear? Professor Biberian kindly made some experiment with our fusion diode. He has a device who keeps the pressure of deuterium constant, because the main problem is the leak of deuterium. And at the beginning, there is a drop in the voltage. It is not a good news, but after some days, there is what it seems to be a stabilization, and it is more interesting. But it is difficult to avoid the deuterium leak and the ensuing voltage drop. We plan to seal a diode in a glass tube and measure the energy for several months simply by copper plating, not with data logger, but with copper plating. It will suffice to weigh the deposited copper to have a reliable estimation of the energy. It is the tube the glass tube we plan to use. It is another model of fusion diode. It is the way to build the fusion diode. Here it's pure silicon, it's pure palladium, it's a little funnel, the container is here. It is a press, the 20-ton press used to press the powder. And it is a seal at the end of the container. We made a special little oven to melt the polyethylene seal in order to improve the seal. Here it's the diode. It's a deuterium filling station near Paris, in our little lab. Here it's a deuterium filling station in Scotland, in another lab. Another team is working on fusion diode, and they have made a diode made by vacuum metallizing of silicon wafer. In one part of the wafer there is gold, in the other part palladium film. But the better way to make diode is probably to make a little disc of semiconducting plastic, gold, and palladium. Here it is an aluminum foil covered in this side by a very thin foil of palladium. Here it is a punch. And on the other side there is a Plexcore semiconducting ink. It is possible to order the Plexcore at Sigma Aldrich Corporation. Well, I will finish because I am a little late. With this technology of fusion diode, it will be very easy to test many alloys quickly and to select the best alloy for our LENR experiment. So just 2 words about the Reifenschweiler effect. Otto Reifenschweiler was heading the neutron generator department of Philips during the 60s, and he noticed an apparent drop of the beta decay of the tritium absorbed by the titanium. He waited his retirement to publish his observation. It is the experimental device. It is a curve obtained by Reifenschweiler. There is a drop of the apparent radioactivity of tritium. The conclusion at the time, the conclusion of Reifenschweiler was a change of the period of the tritium. I'm sorry, but I disagree with this opinion. It is not a change in the decay. It's probably an effect of the lattice. It is late. We are all angry. If we want to discuss of the Reifenschweiler effect, I suggest to discuss in front of my poster in this evening. Thank you for your attention.
We have time for a couple questions.
2 comments. One, it's a very clever device you've got here. And have you looked at the beta battery work that's been done, where you use, in their case, tritium, but they're capturing it into silicon carbide, and they're actually, or silicon nitride, and pulling out?
No, we don't look for tritium.
I'm not suggesting you look for tritium. I'm saying the way in which they manufacture these to load a hydrogen isotope in close proximity, for example, deep wells in the silicon wafer. Another way of manufacturing what you're doing, it's a different way of manufacturing, and it's been done for probably the last 10 years.
These fusion diodes are not the best way to implement this technology, because at the first time we use powder simply because it is impossible to press metal against wafer without breaking them.
The second point.
Excuse me. Now we have, it is possible to order foil of semiconducting plastic, and it will be probably the best way to make fusion diode. It's very simple. A foil of alloy, a sheet of semiconducting plastic, and a fold of gold in the other place. It is possible to make stack of this diode to get a bigger voltage. And it will be probably the best way to make this technology. But at that time, we have no new alloy and we have no commercially available plastic semiconductor.
The second point is, I notice you're using what we call lattice phase materials, and these are the ones that have, other than palladium, one of the ones that loads even higher, and we've used it, is the iron gadolinium-2 D5. So you get even more deuterium into the phase.
Yes, there is probably better alloy. 2 days ago, Professor Violante speak about constantant. To be frank, I was not aware of the capacity of the constantant. It is. Yes, Professor Celani, excuse me. There is no a lot of alloy, and each alloy we must test each alloy in a very constant way, and it is not possible to test each alloy by calorimetry, because to make a good calorimetric experiment takes months. To make a close contact between 3 components is very easy.
Tom Clater and Roger's system is a way to do it quickly, I think.
Professor Marlier.
Since you mentioned my name, I'm obviously in favor of beta batteries, but it's a very clever system. I want to congratulate you. One problem with the testing may be, though, that depending upon the reaction mechanism, which might be different for different metals or alloys, the fraction of the energy that goes into heat versus that's coming out in the betas and so on may be different, and so it could you might mix up some of the data. But anyway, I think it's a very worthwhile thing to do.
Thank you. Thank you for your attention.
Let's thank all our speakers for wonderful talks.